Good afternoon, ladies and gentlemen. My name is Chiravachradej. We meet again today, still discussing about shear force diagram and bending moment diagram. But this time, changing from the application that has only one direction, such as beam, or in fact, we could refer to column, a single piece, single direction element, to a frame. In this case, we are talking about rigid jointed frame. Okay. The topic for today, okay, because we're going to use the same theory on how to create the shear force diagram, bending moment diagram, and the system of thought will be similar. However, the force continuum may be changing a bit, so we will talk about the internal force continuum in case of frame first. Okay. Then we'll see example on how we actually deploy or use the old method, the old two methods that we already learned to apply and use with the rigid jointed frame. Okay. Of course, we have learned before how we draw the shear force diagram and bending moment diagram by functions, and then how to draw it using relationship from the free body diagram to the shear force diagram and to the bending moment diagram. Okay. So let's talk a bit about the internal force continuum. Okay. It used to be just a function of external work done. When there is a system of force adding in or subtracted out, then the concept or the continuing of the function of internal forces changes. Okay. However, with this kind of rigid jointed frame, notice that there are three members here for this frame. Okay. If we look at the continuum here, such in case of direct one direction force continuum, then we will see that in this case, if there's no other external forces acting on this cut, the shear force on the left hand side on the right hand side should be equal and opposite. And of course the bending, well, that is not a line though. I'm so sorry to just expand it. In fact, it should be just a dot. Okay, there's no length. That line has no length per se. Okay, so it doesn't affect, it's looking at one point per se. Okay. Then the axial force on the left hand side and right hand side will be equal and opposite. The bending moment would be the same argumentative. Okay. However, if we look at the joint where the two members meet, the two members that have different direction, in this case we're talking about a column and a beam. Okay. The vertical line represents a column, the horizontal line represents a beam. On that connection, then if we look at that point, again I'm talking about a point. Remember the definition. The definition of shear is not vertical or horizontal. The definition of shear and axial force is in relation to the line of member. Namely, the axial force will be parallel to the member, and the shear force in this case will be 90 degrees to the member. And hence, that's the way it is. The way we draw it, on the member, on the beam, that point connect, that way beam, that way column, correct? So on the connect point on the top, the connection to the member is on the right hand side. Therefore the shear, the axial force and the bending moment are defined according to the alignment of the beam. In this case, you will see the shear, the VR, shear on the left hand side, the axial force on the right hand side, and the bending moment on the right hand side. However, on the same point, apart from connecting to the beam on this side, it also connecting to the column on that side. Therefore, if we look at that part, then the shear force, the axial force, and the bending moment will be defined, the direction will be defined by the column, not by the beam. Therefore, in this case, the shear force 90 degrees to the column, the VB at bottom, VB means shear at the bottom, is actually horizontal because it's 90 degrees to the column. The axial force has to be vertical because it has to be parallel to the line. It has to be on the same line as the column, and of course the bending moment doesn't change. Now notice that compared to the one on the top in the circle, in the red ellipse, the shear on the left, on the bottom, is not equal to the shear on the right hand side. In the red ellipse they are equal. In the blue circle they are not. The shear are not equal to the shear, and the axial force is not equal to the axial force because it's on different line. If you actually do sigma fx, sigma fx in the blue circle will give you that the shear force on the right hand side has to be equal to the axial force at the bottom. Notice shear equal to axial in this case, and sigma fx equal to 0 horizontal. Then you have the axial force on the right and R is equal to the shear force at the bottom, VB. Notice again this time axial force equal to shear. As I said, the continuum of the internal force broke down. Shear is no longer shear. Shear switched into axial force and axial force switched into shear. Therefore, the equation for shear is not possible to continue from the column to the beam. It has to be two different equations because it's not continuing. To be making it more confusing, if we look at the connection, this time we don't have a single match apart from the bending moment, of course, because it has to be the shear on the left hand side combined with the axial on the left hand side equal to the shear on the right hand side combined with the axial force on the right hand side. Well, don't misunderstand me though. When I said the force continuum is broken, it is not really the total force is broken. It is the concept of shear as a continuing function is no longer there. The continuing of the axial force is continuing, is no longer there. How the whole system, disregard of our definition of shear and axial force, they still continue. But however, since we actually define shear force and axial force according to the alignment of the member, it means that you cannot continue the same alignment for the shear or axial force if the member change alignments. Therefore, it is only the shear force continuum is disrupted. The axial force continuum is disrupted, but the total force system is still continuing. It's still the same continuum because there is, in this case, there is no force, no moment adding in or subtracting out. Okay, it's just because of the definition, that's why it's broke down. Now, nevertheless, it just have to say the point that we have to understand the point that with this definition, which we're going to remain using it, if it's broken down, it means that the section from the column to the section of the beam will no longer be considered the same equation for shear, no longer the same equation for bending moment. Okay, so we're going to change it according to the system. That's all. That is the only difference between what we have done before to the frame. Of course, the angle will make it a little bit more confused, but still, the idea will be there. Okay, let's start with the example 1. This is the beam. This is toy frame. It's only 2 member, right? Just for exercise, 2 member. Okay. Notice the force 120 kilonewton per meter. It is 90 degree to leg 3, 3, sorry. 2, 3, or 3, 2, the same, sorry. Okay. Nevertheless, what we want to do is, the question asks us to draw the shear force diagram, the bending moment diagram, using equation, or basically using function. Generate equation first and then draw according to the function. Okay, let's go. Okay, the first step, as usual, find reactions. Okay, when we talk about the angle, we will have to relate the angle when because we have to use sine and cosine, correct? Now, I supply that to system of 90 degrees to link the theta. Okay, here that theta represent that theta. Okay, and all alternative angle will be not theta, theta, not theta, theta, not theta, and theta. Alternative angle will become theta. I have to mark the point that this black line and this black line are 90 degree. This blue line and this blue line are also making 90 degree angle. Okay, for this rule to be correct. But nevertheless, once we work that out, we will keep it for use later. Now, once we define angle, again, we do not actually need the angle theta for this calculation. What we actually need is the sine and cosine values. So I will use it from the triangle 3, 4, 5 in this case to make our calculation simpler. And then I can work out sine theta and cosine theta values beforehand, as shown again on the slide. Okay. Now if I do sigma fx, then I could get R1x, right? This is finding reaction. We've done this before, so let's just go through it. Okay. With sigma moment about 0.3, then I can work out R1y, right? Okay, that's where the value come from. Okay, and then R1y. Don't forget we already have R1x. Okay. Then of course, what do you do here? Why does it move? Never mind. Then sigma fy, then I will get R3y. Or alternatively, you could take moment about 0.1 if you want to. I think it's a little bit difficult for me because it's harder to find 120 kilonewton per meter, the 90-degree distance. That's why I take moment about 0.3 in the first place, because it's easier to define where is the 90-degree distance between the rotation point and the point of the centroid of that distributed load. Okay, let's move on. There. Since we know the load, just to make sure that we get everything correct, we could use sigma m2 to check whether our answer is correct or not. There we are. Okay. Now to generate the function again, we start this time. We discussed before that 1, 2, and 2, 3 must be separate equations. So we start off with 1, 2. We don't cut at 2 though. We don't cut at, well, we cut between 1 and 2. Okay, which is then defined as point A. Once we cut it, we have the usual system, 3 internal forces appearing. Okay, sigma fx, sigma fy, and sigma moment would give you R. But since we already need the shear force and the bending moment, we therefore use only the shear sigma fy for shear and then sigma moment for the bending moment itself. Okay, once we get this, we keep it for drawing the graph later. Notice again that differentiation by bending moment is equal to the shear, but we have proved this before, right? And we also keep the notation there. Then let's talk about member 2, 3 though. Okay, now we definitely have to cut between 2 and 3 somewhere. Again, it's not halfway, it's anywhere between 2 and 3. Okay. Now if we look at it, we discussed this before, we could actually calculate this from either free body diagram. We can draw from A or from point 1 to the cut, okay, as such. Notice how we define X. X is defined following the line of the length of the member, not vertical, not horizontal. X go along with the length of the member, okay, because the shear force diagram, the bending moment diagram show the shear force throughout the length of the beam, not throughout the horizontal or vertical, okay, throughout the length of the beam. Therefore X has to follow the length of the beam. And of course, by definition, shear 90 degree to the cut, N is along the same line of the member, and then bending moment, well, it's still moment about Z axis. Okay, and that identify using sine and cosine, that's 0.6x and 0.8x. Or alternatively, we can look between where you cut 2.3. Okay, now notice that I did not determine that distance B and 3 as x. Okay, because what I want to do is making sure that my x is still running, will still running the same way, 1, 2, and then 2, 3. Okay, I don't have to, but I want to. Okay, mark the word. I don't have to in this case, but I want to. Okay, there we are. Because if we look at that cut, the length from 2 to 3 is 5 meters. So if I define from 2 to the cut as x, whatever have left between from the cut to 3 will be 5 minus x, correct? Okay. Now, if you think back about those two free body diagrams, I believe the one from the cut 2.3 is easier to look at. Therefore, I will start using that one. But this time, to make it even simpler, I will define x as I said I can. I will set x from 3 to b, or where I cut, and of course the three internal forces appear there. Okay. Now let's move a little bit. Then from that free body diagram, 3 unknowns, 3 equations, again we can solve it. Rather than do sigma fx, sigma fy, if we do sigma fx, sigma fy, the problem is that we will have 2 equations, 2 unknown. Because in x you have n and v as well. In y you also have n and v the same. 2 equations, 2 unknown, harder to solve. So what I will do is I will take the summation of all forces in the direction of the shear itself. Then in this case n will not count because n is 90 degrees to the shear. Making that only, I repeat myself, making that only one unknown in the equation as you see at the board. And we can get the answer straight away. And of course, sigma moment over point B will give us the expression for bending moment between 2 and 3. Or in this case, 3 to 2. Okay. Now we have all equations. So we're going to start drawing the graph. And again, differentiate bending moment. This time, notice though, this time differentiate bending moment we get minus shear because our x is go against the proof from last time. Let's go continue. But it still means that our bending moment will still peak at shear equal to 0. Okay, because minus 0 equal to 0. Doesn't matter, it still peak at the same place. So we still can use that concept. Okay, shear force diagram. Again, we draw out the frame of the structure so that we can show the one of the shear on any point of it. Then let's talk about 1 to 2. Okay, the shear, sign convention there between 1 and 2. It has been predetermined when you actually calculate the function. Then the shear between 1 and 2, that the expression we get before is that form. Then of course, how do we draw the graph? Again, first point, last point. Okay, V1 substitute x equal to 0, V2 substitute x equal to 4. What happened in between then? This is a straight line function, right? Then draw a straight line. There's no peak, so we can ignore point 2, the number 2 in the task number 2. Task number 3, tell us where 0 is. That is 0. Again, use the same equation. This time substitute v equal to 0, then we work out x. Okay, that part complete. So let's change and now consider between 2 and 3, or in fact from 3 to 2, because that is the way we set the x. Okay, there. And then that is sign convention again. It determines when you actually draw the free body diagram for the equations. Then shear from 3, again I emphasize my word, from 3 to 2 is that expression. At point 3, the beginning point is not point 2 because we set x from 3 to 2. First point, x equal to 0 at point 3, and of course at point 2 x equal to 5. Okay, and that is the value. Straight line function, connect the line. There's no peak, ignore task number 2. Task number 3, tell us where 0 is. Again, use that equation. We can say where x is equal to 0. The x calculate exactly 3.517. And this x is not measured from 2, it's measured from 3. So tell the direction correctly as well. Okay. If you want to tell it from 2, then you use 1.483. Okay. So that is shear force diagram done. Now again, I emphasized already, the bending moment in both cases we'll peak where shear is 0. Okay, so we mark where is 0 on the bending moment diagram. Give the direction of the positive side, we mean, okay, that is where the bending moment must peak, because we already find it when we do the shear force diagram. Okay, there. Between 1 and 2, that is the expression. How do we draw a graph? Number 1, first point. Number 2, last point. Oh, in this case we do the peak first, okay, and then last point. So that is number 1, task number 1, task number 2, and then task number 1 again. This is parabola, so we draw the parabola curve. There is no cut 0, so ignore task number 3. Between 2 and 3 and 2, sorry, again, the same. First point, the peak, last point, then draw parabola. And that's done. As simple as you think. Well, I hope it looks simple. Okay, so that is how we do it. It's just the same idea, it's just the same concept. It just changed the way things, well, it doesn't change the way, because the way we look at these forces make this direction change, we disrupt the continuum of the internal forces. Therefore, the way we draw the graph alter a little bit, have more consideration to look at per se. Okay. Now, if we look at the same picture again, example 1 and example 2, well, I'm not going to lie to you, it is the same picture, it is the same structure, the same force. The only thing that is changed is that, let's do this again, shear force diagram, bending moment diagram, but this time using relationship instead. Okay, since they are the same, we're going to use the reaction from the first step, from the first example, not from the first step, from the first example, right there. We already calculated, we might as well use it. Okay, now how do we draw shear force? We use that picture to draw shear force, right? Okay, so there we go. That is the free body diagram. Let's find out what is the shear force at point 2, what is the bending moment at point 2 first, to have the reference point. There we are. This time, notice, we do not cut between, we cut exactly at point 2, because we want to know what is the shear force at point 2 and what is the bending moment at point 2. So we know how it ends, basically. That one there calculate so that we know what to start off with. Again at point 2, but this time it's no longer the same beam. It's not on the beam part, it's on the inclined beam part. Therefore, that is the picture. But still the same. Notice the sign convention, because x, this has to be set according to the fixed notation. This time we don't have the freedom to choose. It has to be fixed. Otherwise, again, we have to prove all this relationship again. So if x form being that way, inclined that way, the whole shear box, the whole bending moment box will have to rotate in the same amount. Okay, and then we get that sign convention that is shown on the left hand side of the slide. Now, once we got this done, then again, to avoid having too many unknowns in one equation, I don't want n when I calculate v, so I take the summation of all forces in the shear direction, sigma fv equals 0, and then there is only one unknown, then I get v 2r immediately, and m2 by sigma moment at point 2, about point 2, sorry, not at point 2, about point 2. Okay, next. Now, the shear force diagram, again, we're going to draw it according to the free body diagram. Between 1 and 2, this is the full, the sign convention, that is the full free body diagram, and we did not calculate because I'm not using it, so I leave it as unknown. Okay, then again, it changed with external force, it changed with external work done, right? So basically, it will start off with that, because from at point before 1, it's 0, At point 1, there is a 90 again, shear force is 90 degree to the force that is 90 degree to the member. Therefore, it's not 360, it's 352. Push up, therefore the shear force go up. Then the distributed load, 100 kilonewton per meter, pressing it down. 1 meter, 100 kilonewton. 4 meter, therefore 400 kilonewton. The shear force at point 2 is not 400. The shear force is point 2 is not minus 400. Again, the shear force does not equal to the force. Is not equal to the force. The shear force, the change in the shear force is equal to the total force. Therefore, it is the change. Where is it changed from? It changed from 352.5. Therefore, it becomes minus 47.5. Because it changed, as I said before, 1 meter change 100. 2 meter, another 100 become 200. The change is a constant. Slope is constant. Is represent straight line function changes. Therefore, it is a straight line. Again, the rule doesn't change. Once you draw a graph, it's always first point, second point, peak, end, where it cuts 0. It cuts 0 there, right? But we already know in 1 meter it changed 100. So it can change from 300 something to 0. Then it has to happen within that 3.5 to 5 meter. Basically, that number divided by 100. Normal ratio taking. Okay. Now, again, we have already proved the shear force. We can use that to actually draw the bending moment diagram. Notice on the left-hand side of the picture, the free body diagram, there is no moment applied at point 1. So moment at point 1 will remain 0, and it change with the shear force diagram only. So let's bring up there. Oh, we're going to do the shear. Finish with the shear first, sorry. Okay, never mind. Then look at that. This time when we draw 2, 3, the beginning shear is not minus 47. That is the beginning shear. Minus 178. Okay, that one is the one that push it up there. Okay, again then 120 pressing it down. Okay, there we are. For 5 meters it becomes minus 600 plus those, and then you have the end value. Again, the total force is not equal to the shear force. The total force is equal to the change in shear force. And straight line, because it changed the same amount every single distance, therefore it is a straight line change. And again, there we are. The same idea which we calculated the first time. In this time it comes from 178 minus 178 divided by 120. Now notice that is a number, doesn't look like the same last time, but it is still the same because it measured from different point. Now we will continue and then draw the bending moment diagram. Okay, that is the free body diagram. So bending moment at point 1, as I mentioned before, must be 0. There is no change there. Then bending moment at point 2, well, we calculated this as well. We got the value. Okay, so then we mark it 0 and then minus 160. Okay, notice that we also have to mark where the peak is. Where the peak is where the shear force becomes 0 as usual. Okay, then the first area we considered is from point 1 to where it becomes 0, because that is where it keep increasing. Okay, there. Then the last part, that is when it's reducing. Okay, using the area work out is actually the same. It become equal to moment at point 2 become 610, give or take. Now notice the change though. At the beginning at point 1, the shear force is very high. Therefore, the change in shear force in bending moment is very high. The rate is high, slope high. Where it cuts 0, it has very little slope. Okay, it changed slowly. Therefore, it in the shape. At point 1, notice it goes steep, and then it slow down and slow down. Okay, and that completes the first part between 1 and 2 of the bending moment diagram. Now, the second part from 2 to 3. Notice this time it has to be from 2 to 3, not from 3 to 2, because x is always running from the left to the right, not the right to the left. Therefore, it turns this way. Okay? Then we already calculate. Therefore, this picture tells us that the bending moment at point 2 is equal to 610, which is the same last time, and moment at point 3 is 0. Okay? Bring back up the sign convention, and then the shear force diagram. The same way, calculate the first part first. That one is 610, as we just talked. Then the area. That area is equal to the change in bending moment, right? So you just plot that area into 610. And then the last part of the area is a negative area. It makes bending moment value reducing. Therefore, it becomes like so, because it ends up at 0. And that is the answer. And that answer is the same as the other method, which is the equation. Well, I think that should summarize our lesson for today. As far as I'm concerned, nothing has changed. It's still the same two techniques, the same similar step. It just changed the detail of each step, that's all. From one directional member become multi-directional members. Okay? And when we have to create the whole graph of the whole system, and that is how we did it with both methods still in check. Okay, I hope you have learned, you have enjoyed your learning with me, and thank you for your attention. And I hope to see you again in the next lecture. Thank you very much.